Hello everyone, this is Jun Gao from Queen Mary University of London. Today I'm going to present our work, Frequency-Guided Diffusion with Training-Free Text-Driven Image Translation. So our task is to perform image translation through a text-to-image diffusion process. We classify this kind of task into two categories. The first one is cell-guided translation that aims to preserve the cell, the source image. The second one is to perform structure-guided translation that preserve the structure of the source. We use a target prompt as conditional text for diffusion to tell us what kind of style or structure we want to produce in the output image. We use a source image as the controlling signal to tell the diffusion what kind of style structure we want to preserve in the output. Let's take a look at this example here. For this lady, this is source image and it has the source prompt a sketch. So if you want to translate this image from a sketch to an oil painting, we use another target prompt that says oil painting of a woman. So we get this output. This is the structure guided translation, similar for the cell guided translation, like from a cat to a dog. In this kind of work, the prior words commonly use the attention manipulation to perform the translation, but we argue that the course guidance at spatial level struggle with the style or structure alignment with source. Based on observation that the low or high frequency information actually preserve the cell structure of the image. For example, let's take a look at this figure on the top right. When we perform low-pass filtering or high-pass filtering on the noise latent and then recover the clean image, we actually find that the low-pass filtering results has the color and the high-pass filtering results has finer contour details. So this inspires us to use the frequency information to perform the translation. Another work also uses frequency information, but for the high frequency information guidance, they simply use the high frequency information of the reverse, the inversion, and the low frequency information of the sampling. They use the blending of both components and to perform high frequency guidance. We argue that based on the noise nature of the diffusion, like because the final details but higher frequency information change rapidly during the denoising process, this kind of blending is suboptimal. So this is our framework, and there are three modules here. The first part is the inversion, which is used to preserve the source image information. Then for the low frequency guidance, to perform the cell guided translation, first we perform like high pass filtering on the noise latent of the sampling. Then we perform low pass filtering on the inversion. We combine the filtered noise latent together and then perform the normalization to correct color shifting, because we experimentally find out that the composed latent has different statistics as as the original denoise latent, and this would cause color shifting in the results. So we feed the normalized latent into the denoising model to perform denoising. For the high frequency guidance, to perform the structure guided translation, there are two modules. The first module is a high frequency injection that injects the high frequency information of the attention map from the inversion into the sampling process to preserve the general layout. We also want to refine the details. Basically, we predict the clean image here and we take the original source image here, we calculate the error, and we use this gradient as the guidance to correct the predicting noise and for the refinement. This is the visualization. We show that our method has better balance in terms of the cell structure preservation and image text alignment. For the figure on the top right, we show that as discussed earlier, for high frequency guidance, the blending the straightforward blending scheme from pre-works is suboptimal because it has noise output from the power spectrum. This is the results from the matrix. And this is application. So for the first row here, we show that with the normalization, it helps correct the color shifting here from especially for the yellow color. And for the second row, we show that the high frequency injection and alignment helps with the general layout and details here. This is the thresholds for different for different filtering parameters in our low frequency guidance and high frequency guidance. For low frequency guidance, we show that when we increase the threshold, it generally captures more and more layout information. For the high frequency guidance, we show that when the guidance is between 20 to 30, it has better balance in terms of the structure preservation and the image quality. Yeah. So that's all. Thank you.